Awesome. Okay, yeah. So thanks for having me. My name is Matt. I'm also an intern on the AI Eng team. And the work that I did during this past term was on dataset optimization and benchmarking. And I'll also do a little introduction to forecasting, which is what I'm working on end of this term and then into next term. So here's a quick overview of what I'll go over. So I'll give you guys a brief intro to supervised learning, what our actual problem setup is and our proposed solution, and what our implementation details were with respect to code. Then I'll go through the experiments and talk a bit about the results that we got. And then we'll move into some of the forecasting bootcamp preview stuff. So here's the datasets section. So this is a brief introduction to datasets and supervised learning. So here I've got like a generic AlexNet model and then a zoomed in image of data loader. So essentially in the data loader, what happens is a sampler will calculate the indices to choose from the data set. So like this will be shuffled so it could choose like any number of random indices. It'll send those to the data set. The data set will grab those from whatever your data is stored in, could be like images, text, videos, a bunch of those files. So it'll grab the respective indices with respect to the data, apply the transforms, send those to the collate function along with the target to turn them into stacked tensors, or rather batches of tensors. And then it will feed the data tensors into your actual model. So once the data goes into the model, your model will make a prediction. The prediction with the target will go into your loss function, and then that will backpropagate to the rest of your model. So that's just like a brief intro to how our data loader will interact with our models. Let me just hit next. Oops. So here's our problem. For example, ImageNet is the chosen data set that we wanted to support first because it's so popular. And it's also a moderately large size data set. It's about 1.2 million individual JPEG images. So it's about 400 gigabytes if you haven't cropped the images to 256 by 256. So essentially what your PyTorch dataset class will do is it's a map style dataset. So you'll feed in an index into it. It'll look for that index in its various file paths, and then it will pull the corresponding JPEG from disk and give it to you inside of a tensor, as well as the target going that pairs with the actual index. So this is actually kind of a problem because if you see, we're basically calling open and close a ton of times because they're just like individual JPEG files. So each time we need to read a JPEG, we're going to call open, we'll read the contents, and then we'll close it. But as you can see, if you're training a big model with large batch sizes, this can be a problem. This is really exacerbated by the high batch sizes and the large number of workers. So this results in having like very, very high loads and very, very high frequency on the cluster. So this is really, really bad for our file system. So our proposed solution, first, I'll just like show you the actual layout of the typical ImageNet. So essentially what it is, it's just one folder with two folders for the training and validation set. And these folders just have like a bunch of JPEGs in them. So like JPEG 1 to 1000 could be 1 to 10,000, whatever. It's just a bunch of small JPEG files. But our new implementation, so what we thought would be best would be to contain just one file. We'll have one file paired with another metadata file. And this one file will contain a byte stream. And this byte stream is essentially just a PNG compressed, a lossless PNG compressed byte stream, which we saved by taking the individual JPEGs, turn them into bytes, doing a PNG lossless compression on them, and fitting them and collating them together into one long byte stream. Then we'll actually save the starting byte and the end byte with respect to the index, as well as the target inside the metadata table. So whenever we want to actually access an image, instead of having to use a file path, we'll just call open on the entire data set at the initialization phase. And then if we need to say pull, I don't know, index number 2, we'll go to the metadata table, we'll index into number 2, we'll check the start byte, check the end byte, and check the target. Then we'll use those to slice into the byte stream. We'll actually do a PNG decompression, which is also lossless, in order to get us back to our original JPEG. Also, that should be 2.jpg, not 72, because we indexed into 2. But yeah, so it should be just one call to open and one call to close for the data set, as opposed to a bunch of like tiny little open and closing on small files. So we considered several different backends, but we narrowed it down to two potential backends that we thought would be best. So one was called the HDF5 file format, and the second one was Python's built-in mmap implementation. So the HDF5 file format is basically just a database plus metadata. So it's all in one file too. It can contain like many different types of media, so like images, videos. They don't have to be all the same. It could be like a data set of images and videos. But it also contains a lot of customizable metadata too. And then mmap, which is basically just memory mapping. So it basically just maps a file on disk to virtual memory. It's really complicated. It's like quite complicated and a little hard to explain, but the TLDR is you can actually read directly from hard disk to your program because it's mapped in virtual memory. So these are the backends we'll be comparing against the default PyTorch implementation of ImageNet. So another consideration we had was we wanted to make sure that users didn't have to like go through any crazy logic or like add so many lines of new code. We just wanted them to have to choose or have to change only like 1 or 2 lines. So before, it's just the standard, from Torch Vision datasets, import ImageNet, create your dataset, and then give it to the data loader. But after our changes, all it should be is instead, you're pulling from vector datasets. You're going to import the custom dataset, and you're just going to create a new custom dataset object and then feed that to the normal PyTorch data loader. So just 2 lines of code, well, maybe 3, but so before testing our implementation, actually, I'll go through the hyperparameters that we were going to vary. So I know like everyone who's ever trained a model has obviously always used num workers and batch sizes, but I'll actually go through what they do. So essentially, let's assume that you say, oh, I want to use num workers equals 4. So what does that actually mean? So in your data loader will see, okay, num workers equals 4. So when your main process says, okay, let's create a data loader and let's use it to give data to our model. Data loader will call fork, which clones the main process. Let's say if you have enough 4 workers, then you'll have 4 processes, each corresponding to 1 worker. The workers will also get their own batch indexes. So worker number 1 will get the first batch, worker number 2 will get the second batch, and so on. It'll take those indexes of batches and it will request them from the dataset class. The dataset class will give back the corresponding batch data to the processes. So then you'll have 1 to 4 batches. So in this case, we'll have 4 batches. And then once the workers receive those batches of data, it'll actually feed those batches back to the main process. The workers will all exit, and then the main process will take those 4 batches and give it to the model. So that's where num workers and the batches come into play with respect to our dataset and data loader. So here's your experiments. Our objective was to load the entire ImageNet training set and to compare the time elapsed across backends with respect to the certain hyperparameters. So like the backend, the number of workers, and the batch sizes. So we ran 2 good experiments. So one was on an isolated regular CPU node. So it's just a single user trying to load the dataset once. And then our second experiment was multiple users trying to access the same dataset. So for example, on the picture on the right, you'll see like 5 users trying to access the same dataset and try to load it at the same time. So this would have been like the closest conditions to just loading on the normal cluster. So here's the results for the first experiment with the single user. So we swept across 4 parameters for the number of users, so 0, 4, 8, and 12. And we also swept across some select batch sizes, so 1, 16, 32, yada, 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 until 4,096. So the default is in blue, the HDF5 is in red, and the mmap is in yellow. So as you can see, the defaults still beat everything, but as we raise the number of users, the difference between the loading times actually shrunk quite a bit. So we wanted to see what would happen if we increase the load even further. So let's add some more users trying to access this data set. And here's the results for that. So we actually fixed the batch size in this and fixed the number of workers. These were from our experiments. This was actually the fastest loading times we would get with respect to those 2 hyperparameters. So we just fixed them across the entire experiment. So as we added the number of concurrent users at once, you can actually see that mmap scales the best with the most number of users, and the default implementation scales the worst. So this is what we wanted to see. So essentially what essentially what was happening here was we're increasing the amount of background traffic with respect to just like people in general on the CPU doing things, but also the amount of people trying to access the same data set. So this would be, this is very important for scaling with really, really popular data sets like ImageNet, where like, even let's say like, even if you're just technically one user, you queue up like, I don't know, maybe 80 experiments, 100 experiments or even more, trying to access the same data set with huge batch sizes, huge number of workers. This is completely realistic. So that concludes the experiments we actually finished. So our next steps would just be finishing the development of the caching mechanism. We're just like in the actual implementation is actually done. We're just doing some testing. And then we just need to do a brief cleanup of the GitHub code, but it's mostly already nice. And then the next step would be reaching out to researchers to find out what other potential data sets other than ImageNet we can actually implement this for. So for example, we were actually thinking of implementing Celeb, maybe like LSUN, like any data set like those. Also, I think it's usually the image and maybe video data sets we want to support, because those ones are usually a lot worse to load than most of the text data sets that I know of. And then I'll just take you guys through a quick little preview of the forecasting work I'm going to be doing. So this is just a little introduction to spatiotemporal forecasting. So what is spatiotemporal forecasting? So it's essentially what happens is your data is three-dimensional. So you have a height, a width, and a time axis. But the thing is, because it's an image in varying through time, we can actually leverage intra-image covariances between regions and pixels to make very strong predictions. And we can also leverage the covariances across time. And this allows us to make like very, very good forecasts, as opposed to like maybe typically like multivariate, where there could be very, very sparse relationships between space and spatial variables. So in this diagram below, you can actually see the context that's outlined. So typically a model would take in that context, do whatever it needs to do, and then predict a time series target, which also is a bunch of images which vary through time. So for example, some of the use cases we could use this for would be nowcasting precipitation, forecasting global weather patterns, forecasting potential adverse weather events, electrical loads on power grids, could use like a graphical neural network for that, and also traffic conditions. So on the right, there are just some GIFs that I made of a potential data set that we were going to use called Weather Bench. So the top two are actually cloud cover. The one on the left, I've just underlaid the actual continents just because it looks pretty. And then on the bottom left is the U component of the wind speed. And then on the bottom right is the temperature at 2 meters above sea level, so about human height. So there's three interesting models that we found. So one was called the DGMR by DeepMind, so Deep Generative Model of Radar. So it's an extension of the GAN network of family, so the Generative Adversarial Network. Essentially what it is a conditional GAN where it takes in the context into the generator, and the generator will be constrained by the discriminators too. So it'll be a temporal and a spatial discriminator. So this ensures stability and consistency in forecasting in both the spatial dimension and the temporal dimension. So a use case for this would be a precipitation prediction at a province and state level to about national scale, and also nowcasting too. So another model would be the Google AI's MetNet 2. So in this model, they actually embed the spatiotemporal context. So like kind of like the 4 frames that go into the generator for the DGMR. They embed that using convolutional LSTMs to give it some notion of time, I believe. And then it uses a WaveNet backbone over these so that it can expand its receptive field over embeddings so that it can see a much larger area than would usually be allowed. So a use case for this would be also nowcasting across multiple provinces and states about that level. And then the third method is a little bit more experimental than the past two, but it's called long-range transformers. So it could actually be applied to either spatiotemporal and pseudo-spatial-temporal multivariate tabular data. It's pretty versatile. It's basically just converting everything into a bunch of embeddings and then just doing standard attention over the embeddings. So a potential use case for that would be multivariate spatiotemporal forecasting. Thanks for listening to my talk. I'd like to thank Gerald Shen for strong collaborations with me on the datasets project. And here's just some links to the references that I used in my talk. Thank you.